What is a compound inequality? Well, a compound inequality is any combination of two or more inequalities joined by either an and or an or. And the strategies we use to solve these compound inequalities are going to be very similar, but they're going to interact with one another, either by being joined by an and or an or, and we're going to discuss how that works right now. So let's take a look at our very first example, where we have a is greater than or equal to negative 4, and a is greater than or equal to 7. And here's what the strategy is going to be every time. Let's start by graphing each of these individual inequalities first, and then we'll explore how they interact with one another. So for a is greater than or equal to negative 4, let's do that in blue. We'll have a negative 4 over here on the number line, and we'll fill it in, and our arrow will go to the right. So any number shaded in blue is going to make this inequality true. For a is greater than or equal to 7, let's do that one in red. So we'll have a 7, we'll fill that in as well, and that arrow also goes to the right. So any number shaded in red will make this inequality true. Now what does this and mean? Well, to be a solution to a compound inequality with and, a number must be a solution to every single one of the individual inequalities connected by and. So in order to be a solution here, the number must make both this inequality true and this inequality true. And if there was a third inequality, it would have to make that one true as well. It's got to make them all true. So let's take a look at our number line. So for instance, these numbers in this region out here to the left, these numbers make neither this statement true nor this statement true, so they're definitely not going to be solutions. Let's get rid of them. These numbers between negative 4 and 7, well, they're shaded in blue. So they do make this statement true, but they are not shaded in red, so they do not make that statement true. And since they don't make both of them true, these numbers are not going to be part of our solution set. So let's get rid of that. Now these numbers out here, numbers greater than or equal to 7, are shaded in both blue and red. That means they make both this statement true and this statement true. They make all of the statements true, and therefore this is going to be our solution set over here, this region of numbers. Now, how do we tell our reader that? We have to do it in two ways. The first way is to tell them that this is the solution set graphically. And what we're going to do is we're going to shade that region of our number line, just like this. So that tells our reader that these numbers, they're going to be the solutions to this compound inequality and nothing else. But it's also important that we give our reader a written statement of the solution set. And so I would say in this case, it appears that what numbers are solutions? All numbers greater than or equal to 7. So it's important to write again an explicit statement of our solution set in addition to what we've done graphically. All right, not so bad. Let's proceed. So in our second example, we've got 3/2 is less than or equal to a, or a is greater than or equal to 5. So the big difference here, we've got an or. Let's see what happens. Same strategy as before. Let's graph these individually first. So for this one, we'll have negative 3/2 on the number line. We're going to fill that in, and our arrow is going to go to the right. For a is greater than or equal to 5. 5 is our boundary number. We're going to, again, solid dot, and we're also going to shade to the right. So interestingly, we note that our graph looks very similar to our first one. We have two arrows going to the right that do have a region that overlaps. Okay, but now instead of an and, we've got an or. So let's talk about what that means. All right. To be the solution to an or compound inequality is actually much easier than being the solution to an and inequality. In order to be a solution to an or compound inequality, the number has to make at least one of the individual inequalities true. So if it makes one of them true, it works. If it makes both of them true, it works. The only way to not be a solution to an or compound inequality is to make none of the individual inequalities true. So let's take a look at our number line. These numbers out here to the left of negative 3/2, these numbers aren't shaded in blue or red. They make neither of these true. These guys are not solutions. All right, let's get them out of here. What about these numbers from negative 3/2 to 5? Well, they are shaded in blue, meaning they make this statement true. But they do not make this statement true because they're not shaded in red. However, since we're working with an or compound inequality, that's good enough. If you make one of these guys true, you're a solution to the compound inequality. So a little bit easier with or than it was with and. So these guys are going to be solutions in there. Okay, so these guys are solutions. What about these guys over here? These guys are shaded in red and blue. They make both of these statements true, so they're definitely solutions as well. And so if we want to shade our solution set, all of these numbers are going to be solutions to this compound inequality. And of course, they go on and on forever in this direction. And so there's the visual representation of our solution set. What are these numbers? Well, if I were to state the solution set with a written statement, I would say all numbers such that negative 3/2 is less than or equal to a. Again, remember, really important to give your reader both a visual representation of the solution set and an explicit written statement. So that's the general way to handle and or compound inequalities. And so as we make our way through the next examples, I urge you, why don't you see if you can do them on your own or predict what the solution set will be. But of course, I'm going to walk you through them as well. All right, in our fifth example, same strategy as always. We got to start by graphing the individual inequalities and then seeing how they interact with one another. So there's a 3, a is greater than or equal to 3. 9, a is less than or equal to 9. Oh, interesting. Okay, this is a situation we have yet to see yet, because now we've got arrows going in opposite directions, whereas in every one of our previous examples, they've all gone in the same direction. So now that they're going in opposite directions, well, in order to be a solution, the number must make this statement true and this statement true, because we're dealing with an and statement. So let's take a look on the number line. Well, these numbers out here make this guy true, but they don't make this guy true. So they're not going to be solutions. Sorry, no luck. These numbers in the middle, they are shaded in blue and red. They make this statement true and this statement true. They are going to be solutions. Awesome, awesome, awesome. Let's keep that in mind. And these numbers out here, well, they're shaded in blue, but not red. So unfortunately, since they don't make all the statements true, they're not going to be a solution. So it appears that our solution set is in this region just here in the middle. And it's kind of bounded, right? It kind of starts at 3 and it ends at 9. And it's everything between 3 and 9. And so here is where the statement of the solution set gets a little tricky. What I would actually say is, if I look at this intuitively, I'd say, well, any numbers between 3 and 9, including 3 and 9, are going to work. And this is how we write it. We write it like this. 3 is less than or equal to a, which is less than or equal to 9. Now, this is a very different statement from any we've made before, and this kind of longer statement of a solution set happens only when we have a solution set that looks like this. It's bounded. It starts somewhere, and it ends somewhere. Usually, like before, all of our solution sets kind of went on forever and ever to the left, or they went on forever and ever to the right, and they had different looking statements of the solution set. But this guy, since it's bounded, since it exists only starting here and ending there, that's why this has a more interesting statement of the solution set. So just a heads up. All right, continuing on. All right, here we go. Let's graph these individual ones first. So a is greater than or equal to -7, so -7. And a is less than or less than -1. Okay. So now we got to say, well, here's the deal. To be a solution to an or compound inequality, if you're shaded at all, if you're hit by red or blue or both, then you're a solution, right? As long as you make at least one of these guys true. And I'm looking at this number line, and, well, these numbers are hit by red. These numbers are hit by red and blue. And these numbers are hit by blue. So that means every single number is a solution because every single number makes at least one of these guys true. And so in this situation, our solution set, you could shade the entire number line if you want. Just going on and on and on forever and ever. And you would say the solution set, this is actually most important, is to write that all real numbers are going to be solutions in this case. So this is another interesting example. And what I would say is, I shaded the number line here to show that it was all real numbers. This is the one time when, if you would like, you don't have to shade your solution set because it is implied by this statement, all real numbers. Every other time, I would really, really, really shade it too. Okay, here we go. More examples. Okay, here we go. Again, first thing I would do, let's graph the individual inequalities. A is less than or equal to -4. And a is greater than or equal to 1/2. So 1/2. Awesome. All right, so now since we're looking at an and compound inequality, we're looking for numbers that make all of these statements true at the same time. We're looking for numbers that are shaded both blue and red at the same time. All right, let's check it out. Well, these guys make this one true, but not this one. Womp womp, not solutions. Okay. These guys make neither of them true, so definitely womp womp, no solutions. Okay, what about these guys? Well, they make this true, but not that true. So womp womp, not solutions. And so there are no numbers at all that make both of these statements true at the same time. There are no numbers that are hit by both blue and red at the same time. There are no solutions to this compound inequality. And so there's nothing to shade because there are no solutions, but it's really important that we write to our reader there are no solutions. And if we use our intuition, let's think about it. It's impossible to be less than or equal to -4 and greater than or equal to 1/2 at the same time. It's just not going to happen. So no solutions in this case.